with quantum numbers. Quantum numbers. There are four quantum numbers. So I like to think of the four quantum numbers as being an electron's address. An electron's address. So what's the address of the house you grew up in, Alan? Give some fake address, I guess, if we're filming this. Give me a fake address.
123 Fake Street.
123 Fake Street. So I asked a student that once and told him to make up an address, and he says 22 Bald Street. Look straight at me. It's pretty funny. But so 123 Fake Street. So you live at 123 Fake Street? Wow, that's crazy, because I lived at 123 Fake Street. But I'm pretty sure I didn't live with you. So notice no two people can have the exact same address unless they're living in the same house. So the same locale. So same thing with an electron. So no two electrons can have the same address, which ultimately means no two electrons will have the same set of four quantum numbers. That's what the Pauli exclusion principle says. So no two electrons will have the same four quantum numbers in an atom. So before we get into what these quantum numbers are, we should kind of delineate one major thing here. So if you look at the first shell, so in the first shell, I'm going to need a little more space for this. So in the first shell, all there is the S subshell. There's nothing else. And the S subshell just has one orbital that can hold two electrons. So each vertical line here is going to represent an orbital. So in the second subshell, you got the S's, and then a little higher in energy, you've also got the P's. So it turns out every time you go up to another energy level, or shell number, you actually get a new type of subshell. So shell number 1 has only S. Shell number 2 has S and P. Shell number 3 has what else we got? Shell number 3.
D.
D. What about shell number 4?
SPDF.
Yeah, S, P, D, and F. If you also note, so there's only one S orbital per S subshell. There are 3 P orbitals per P subshell. There are 5 D orbitals per D subshell. How many F's are there going to be?
7.
7. Notice 1, 3, 5, 7. So every time again you go up a shell number, you get a new type of orbital, a new subshell. So shell 1, S. Shell 2, S and P. Shell 3, S, P, and D. Shell 4, S, P, D, and F. So, and again also, if you go across the subshells, the number of orbitals goes from 1, 3, 5, 7. It just counts on the odd numbers. So what about shell number 5? What does shell number 5 have?
Same as the previous.
Again, every time we go up a shell, we get a new type of subshell. So 5's got S, P, D, F,
G.
and G. Anybody ever heard of a G orbital? No. They do exist, oddly enough. We don't have, in the ground state, nobody's got any electrons in them. But in the excited state, we can actually put an electron up into a G orbital. They do exist. So nothing you'll have to worry about. So if we did, though, worry about the G orbitals, how many G orbitals would be in the 5G subshell? 9. 1, 3, 5, 7. And the G's would have 9. Sweet. So we've got the pattern now. Once we understand this pattern, it's a little easier to make sense of the quantum numbers. So let's say we were trying to find an electron right there. We want to identify that electron's address. So, and again, his address is the set of 4 quantum numbers. So if we want to find his address, so the first quantum number, so if you look at your table on your sheet, it'll make it a little easier to see. But the first quantum number is N. So N is the principal quantum number. So it's your principal quantum number, and it gives us the shell number. So in this case, if we look, those are delineated by 1, 2, 3, 4. It's that principal quantum number. Just gives us what shell of electrons are we actually in. So if we look here, so those are our shells. That's what N ultimately tells us. These are also, oddly enough, the same exact numbers we saw on the Bohr model of the atom. So Bohr's model of the atom with the big circular orbits, so where we had the first shell, second shell, third shell, fourth shell, was the same as this principal quantum number. Turns out his model only works for any atom that only has one electron, like hydrogen. So it turns out if you only have one electron, your S's and your P's, your S's, P's, and D's, or F's or anything, will all be equal energy. That only applies to if you have one electron, only applies to hydrogen, doesn't work for anybody else.
Is that only one electron in your outer shell? Or
Only one electron total.
Oh.
So it turns out once you get more than one electron, the Bohr model of the atom is useless. So it doesn't work anymore. That's why he would kind of give him some props, because he explained some things that involved hydrogen. Turns out it just didn't explain anything else. It turns out it explained hydrogen not because it was right, just by odd coincidence that the math worked out. So we give him props for being wrong. I don't know. Go figure. All right, the next quantum number is L. So L is called the azimuthal quantum number. It has a really funky name, which you probably haven't heard in any other context besides this right here. Because it has such a funky name, this is the one they often ask you about. They say, what would the azimuthal quantum number be? So just because, it's the one that's easiest to forget because it's the one with the hard name. So good one to sear into your memory banks. But this azimuthal quantum number will tell you the subshell. Didn't want to use blue there. So it's going to tell you the subshell. It's going to tell you if you are in an S, a P, a D, or an F subshell. So the way it works with L. If you're in an S orbital, L will have a value of 0. If you're in a P orbital, L will have a value of 1. If you're in a D orbital, L will have a value of 2. An F orbital, then L will have a value of 3. So N tells us which shell of electrons we're in. It's L that tells us if we're in an S, a P, a D, or an F subshell. Next quantum number is M sub L. So M sub L is called the magnetic quantum number. So the magnetic quantum number, ultimately you'll see it most commonly explained as it tells you the orientation in space. Which is kind of a little deceptive of what it really tells you. It actually identifies a specific orbital. If you notice, like with your 3 p orbitals in any given shell, typically we define them as px, py, and pz. They have that dumbbell shape we talked about earlier. And they lie either on the x-axis, on the y-axis, or on the z-axis coming out at you. So they have different orientations in space. So it is the value of M sub L that tells you which of those specific orientations, or which of those specific orbitals you're actually going to exist. So if you notice, let's say I was in the S subshell. So how many orbitals exist in any given particular S subshell?
Just one.
Just one. Being just one, I only need one value for M sub L. So we find that when we get to the ranges here, so we'll find it works accordingly. So we'll come back to that in just a sec. If we look at, last but not least, M sub S. So M sub S is called the spin quantum number. So it simply just identifies what you often see is, we draw the arrow pointing up or pointing down. That's a differentiation of that spin. So this very nebulous concept called spin doesn't mean an electron is actually spinning around or something like that. Turns out it's just an inherent property of the electron. They called it spin. They could have called it anything. So we look at the range for each one of these values. So your principal quantum number, what's the lowest possible number you can have for the principal quantum number?
1.
Yeah, just 1. Start at the lowest shell, shell number 1. How high can it go? We've only showed up through the 4th shell here. In principle, how high can it go?
We don't know.
We do know.
Infinity.
Yeah, it actually doesn't stop. It just keeps going all the way to infinity. So your principal quantum number, in theory at least, start at 1 and go up to infinity. If you look at your azimuthal quantum number, so we look at the azimuthal quantum number always as it relates to the principal quantum number. So if we look in the first shell, when n equals 1, what is the only possible value L can have?
0.
0. If we look at where n equals 2, what are the possible values for L?
0, 1.
0 and 1. When n equals 3, what are the possible values for L?
0, 1, 2.
0, 1, and 2. And for n equals 4?
0,
0, 1, 2, 3. So the lowest possible value for n is always going to be 0, but it can take on all the integer values up to a maximum of 1 less than n. So if n is 4, then it can go all the way up to 3. Notice it doesn't mean it has to be 3. It could still be 0, 1, 2, or 3. A lot of students get confused and just say, oh, it's n minus 1, so it's 3. No, it's 0, 1, 2, or 3. It's up to 3. So it's just the integer values. So again, n takes all the integer values from 1 up to a max of infinity. Just keeps going. No real maximum. L is always limited by what n is. It can start at 0 always and go as high as 1 less than n. So your magnetic quantum number. So again, your magnetic quantum number tells us which specific orbital we're in. So if you're in an s orbital, so if you're in s subshell, I should say, there's only one orbital. So you only need one value for m sub L to identify that orbital. But if you're in a p subshell, how many orbitals are there? There's 3. So you need 3 values for m sub L. So it turns out that m sub L is bounded, just like how L is bounded by whatever the value of n is, m sub L is bounded by whatever the value of L is. And it goes from negative L all the way up to positive value of L. So here, if I'm in an s orbital, what's L? So if I'm in an s subshell, what is the value of L?
0.
0. And so m sub L could go from negative 0 up to positive 0. Again, these are integer values as well. Well, negative 0 and positive are all just 0, which is good. I give only one value because I only needed one value to identify one orbital. But if I'm in a p subshell, what's the value of L?
1.
Yeah, it's 1. And so what possible values could m sub L have if L is 1?
Negative 1, 0, or 1.
Yeah, negative 1, 0, and 1. 3 different values, 1 for each of the 3 different p orbitals. So if I'm in a d subshell, what's L? 2. What values could m sub L have?
Negative 2, negative 1, 0, 1, 2.
Yeah, negative 2, 1, 0, 1, 2. 5 different values, 1 for each of the different orbitals. So last but not least, you got your m sub s. So in your m sub s, simply just has a value of either plus 1/2 or minus 1/2. That's it. There are no other options. So oftentimes we think of this as being like spin up and spin down, but it's really somewhat arbitrary. Just have opposite spins. So again, when we write an electron, that's an arrow. Sometimes we have the arrow point up, sometimes we have point down. That is what m sub s helps us differentiate.
Is there a standard way of, like the first way you do it, they're always up? Or?
Not at all, not at all. There is no standard way of doing it. The first one doesn't have to be up. It could be down. The one thing is if you start putting electrons, if I put 3 electrons in the p orbitals, so each of the orbitals gets 1, they're either all up or all down.
Right.
So, but there is no standard way that one has to come before the other. For some reason, you'll usually see it written as up before down, but it's arbitrary.
How are you going, on a test, how would you designate whether it's plus or minus?
Cool.
Yeah.
We'll get there in just a sec. So we're totally going to see how can they ask me a question based on quantum numbers. Well, the first way is they could say, which of the following would be a possible set of quantum numbers for an electron in a 3D orbital? Well, if it's in a 3D orbital, what does n have to be?
That's 3.
has to be 3. What does L have to be?
2.
Has to be 2 if it's in a d orbital. So, but does m sub L have to be a specific number? What could m sub L possibly be?
Could be -2 or -1, 0, 1, 2.
It could be -2, -1, 0, 1, or 2. So actually, m sub L just has to be one of those numbers. Like if I picked -2, that would be a possibility for an electron in a 3D orbital. What about m sub s? Does m sub s have to be a certain value? No, it could be either +1/2 or -1/2. And so if this was, this would be a possible right answer for an electron in a 3D orbital. We never actually go so far as to identify each individual orbital as being a certain value of m sub L. We never go that far. And so the first two, yeah, you got to nail those. But then you got options for m sub L and m sub s. You just got to make sure it's one of the possible options for an electron in a 3D orbital. So that's one way we can see this. Could just say which of the following corresponds to, possible set of quantum numbers for an electron in a 3D orbital. So the other way you might see this. So again, if we look at a set of quantum numbers, n followed by L, followed by m sub L, followed by n sub s, you may simply get a question that just says, which of the following is a possible set of quantum numbers? Can this set of quantum numbers exist?
No.
What's wrong with this set of quantum numbers?
The last one.
MS.
Yeah. Why is the last one off? What's wrong with it?
Such an integer should be either +or -1/2.
Yeah, it's got to be either plus or minus 1/2. So as a result, if I get a question simply looking for a possible set of quantum numbers, it's easier to rule out the wrong choices than to find the right one. That's the first place I look. That's not plus or minus 1/2, it's wrong. So this is not a possible set of quantum numbers. So is this a possible set of quantum numbers?
No.
No,
Why not?
because the L is equal to n in that case. And it has to be n minus 1 if it's in
Yeah. So if n is 3, then the highest L could be is 2, n minus 1. Can't be 3. So this is also not a possible set of quantum numbers. Could this be a possible set of quantum numbers?
No.
What's wrong with this one?
the m sub L is limited by L.
Yeah. If L is 2, then m sub L can only be either -2, -1, 0, 1, or 2. It can't be -3. Cool. So these are the three places I look. I look at m sub s, I look at the relationship between L and n, and between m sub L and L to find the ones that don't work. So as a result, all three of these are not a valid set of quantum numbers.
Would they ever give you like an app and say, what's the, which one of these is a possible quantum number configuration for the atom?
Well, you can't have a possible set of quantum numbers for an atom, because notice
It's
4 quantum numbers identify a single electron, whereas an atom typically has many electrons. But they could put it like, which set of quantum numbers identifies an electron in the valence shell of this atom, or something like that. That would be just like how we did before, where we said identified like a 3D electron or something like that. You just have to identify which one's the valence shell.
Okay. In the exception rule of
Chromium,
you're right.
copper, and stuff.
Is the D still the outer valence shell, or with the 1s?
Cool, good question. When you look at valence electrons, usually it's everything past the last noble gas. So, however, if you fill up the D electrons, they are typically not considered valence electrons. So, if you've got, say, chromium, So if you see chromium, are the d electrons full?
No.
Then they're typically counted as valence. And chromium would be considered to have 6 valence electrons. So if you look at something in contrast to say like bromine. Ooh, don't want to go there. What is bromine? It's electronic configuration for bromine.
Argon.
It is argon, okay.
And then 4s2, 3d10, and then 4p5.
Perfect. So argon would be viewed as having 7 valence electrons. So if the d orbital, if the d subshell is full, they're typically not considered valence. So here, because 3ds, which hold 10 electrons, got all 10 full. They're not valence electrons anymore. And so bromine is just viewed as having 7 valence electrons.
Okay. And so you would have to be able to identify that it could have been in the S or the P.
Exactly. So here with argon, if you had said which is possible set of quantum numbers for a valence electron of bromine, N's got to be 4, but L could have either been 0 or 1. Questions? All right, let's talk very quickly about the ground state or the excited state. So if we'll use bromine as our example right there. So bromine's got the electronic configuration argon, 4s2, 3d10, 4p5. So but let's say I take this same bromine and I shine some light on it. And I shine just the right amount of energy of light on this thing. So what has been the influence of shining light on bromine here?
Creates a radical.
Doesn't necessarily create a radical per se. Wouldn't necessarily call it a radical. It may already have had unpaired electrons to begin with, so it may already have been.
It creates a new shell.
So it doesn't necessarily create the shell, but it puts the
Builds.
electron in that new shell. So we call it a promotion. So the electron gets promoted to a higher energy shell. So when you have electrons in higher energy shells by this promotion process, when they absorb light, we call this the excited state. Whereas our standard way of figuring out electronic configurations are always figuring them out for the ground state. So if you look, ignoring our 5 exceptions, but for everything else, if you start putting electrons in a higher energy orbital before the previous one is full, that's the excited state. And you get to the excited state by absorbing light. So that answers your question you asked earlier about, which of the following, how did it get here? To get to an excited state like this kind of electronic configuration, you've got to absorb light. So if I go from the ground state to an excited state, I absorb light. If an electron falls back down and I go from the excited state down to the ground state, then I would be emitting light. So that's where the absorption and emission spectra come from. Just are you going from ground state to excited state, or excited state back to ground state? Lower energy to higher energy, or higher energy back down to lower energy? So absorb one way, emit the other. Questions?
Is there a way to designate that without drawing out all the electrons? Like, is there a way to notate that bromine is in an excited state if you're just to have the BR?
If you just have the BR,
Yeah.
sometimes you'll see a little asterisk written right next to it. If it's in an excited state, you don't know exactly what. It's not well defined how that is. So that's misleading too, because sometimes you can be in an excited electronic state or an excited nuclear state if you're like undergoing some nuclear process. And sometimes you'll see an asterisk used in either case. So it could be one of two things if you see the asterisks. Either excited state if you're looking at the electrons, or excited state if you're looking at the nucleus itself, it's undergoing nuclear chemistry.
Is that something we're likely to see on a test?
You may see it, not necessarily on a test. If you're taking the MCAT, you may have a passage that just uses kind of that standard notation, especially more relevant to nuclear chemistry than to this kind of stuff. So, but on the DAT, not so likely.
Okay.
Cool. So we're going to switch gears here. So we're going to start talking about nuclear chemistry. All right, so nuclear chemistry. So nuclear chemistry, very different. So you get one little chapter of nuclear chemistry, usually taught at the end of second semester general chemistry, different from all the rest of the chemistry you typically get. Typically all the rest of general chemistry, as well as organic chemistry, deals with the chemistry of the electrons. So when you make and break bonds, which is what you do in standard chemical reactions, that's the chemistry of the electrons. Bonds are made of electrons. So but nuclear chemistry, so we largely ignore electrons altogether. It's the chemistry of the nucleus. So these are the reactions you deal with in like radioactivity, or nuclear reactors, or fusion going on at the center of the sun, things of this sort, nuclear bombs. So the nuclear chemistry, and typically a lot more energy being available in dealing with nuclear chemistry. So in nuclear reactions, mass is converted into energy. So we'll look at the energy conversion very briefly later with E equals mc squared. That's the energy mass conversion. When you convert mass into energy, huge payload. A little bit of mass being converted into energy, so it goes a long way. A little mass is equal to a lot of energy if you actually convert it into energy. So like, you got a Corolla. Your Corolla holds like 12 gallons of gas. You might make it 400 miles. So you might make it 400 miles. You're like, is that good efficiency of your gas and stuff like that? So you might think so. It's Corolla. I got 35 miles per gallon. That's great, So, however, if you were somehow able to turn all of your fuel into energy, so you could probably circle the Earth several times in your car. So you're like, fuel efficiency, well, you're doing chemical reactions. So you're using bond energy when you're doing, burning your fuel. So in your car, if you were able to actually have a nuclear-powered car, which probably would be the greatest idea, but you actually get much better gas mileage. All right. So your nucleus. What lives in the nucleus again?
Protons and neutrons.
Protons and neutrons. What's the charge on a proton again?
1.
Plus 1. Charge on a neutron?
0.
0. So you got this lovely nucleus with protons and neutrons. How does a neutron feel about another neutron? Doesn't care. Neutron, who cares? How does a neutron feel about a proton? They actually kind of like each other, oddly enough. Some weird kind of way. So, but how does a proton feel about another proton? Yeah, don't like each other. They repel each other. So this nucleus has a bunch of protons typically in it, which don't like each other, repel each other. And so this nucleus is actually being held together. So if we look at this, what's holding this nucleus together? Sometimes you hear it referred to as the strong nuclear force. Sometimes simply just put the strong force. So one of the 4 fundamental forces of physics. And it's what's holding these protons and neutrons together. So sometimes you'll hear this summed up also, we'll talk about this later, as the energy supplying, the energy that this strong nuclear force supplies is called the nuclear binding energy. So if I push on this board here, I push on it, I'm pushing with a force, and I'm supplying energy when I'm pushing it. So the nuclear binding energy is just the force So it's the energy supplied by this strong nuclear force. All right, before we dive too far into a discussion of nuclear chemistry, there's a few symbols you got to be familiar with. So the first one is alpha. So an alpha particle is the equivalent of a helium nucleus. It's got an atomic number of 2, it's got 2 protons. It's got a mass number of 4 because in addition to those 2 protons, it also has 2 neutrons, this is the same as what a helium nucleus has. So why is it the same as a helium nucleus but not a helium atom? What does a helium atom have that a helium nucleus doesn't?
Electrons.
Electrons, yeah. So an alpha particle doesn't have any electrons. It's just the equivalent of the nucleus of a helium atom. So you also got P. What do you think P represents?
Photon.
A proton. What's the atomic number of a proton? 1. And the mass number?
1.
Also 1. Cool. You also typically see a neutron. So N for neutron, little lowercase n. What is the atomic number for a neutron?
0.
And the mass number?
1.
Sweet. So, a couple more, you're going to see an electron. You actually use the symbol beta to represent an electron. What's the atomic number, or i.e. charge, of an electron?
-1.
-1. What about the mass number?
0.
0. Again, does this thing actually weigh 0, weigh nothing? No, it's just so small we round it down to 0. But remember to actually just truly have a tiny mass. So you might also see this written with the letter E. So sometimes you'll hear loosely an electron referred to as a beta particle, represented by the Greek letter beta. So an electron, a beta particle, same thing. Cool. You may also see its antimatter particle, which is this guy. So this thing is called a positron. And we'll talk a little more specifically about this when we start talking about routes of nuclear decay. But it's just the antiparticle of an electron. It still weighs the exact same amount of electron. We still round it down to 0. But it has a +1 charge instead of a -1 charge. So it really is just a positively charged electron.
How do you get that?
How do you get that? There are certain nuclear decay processes that actually result in their production. So, but as soon as a positron is created, as soon as it bumps into an electron, so a particle and its antiparticle, when they collide, destroy each other. They actually cease to exist once they collide. And it gives up a bunch of energy. So we actually don't ever see the positrons. We see the result of what the positron leaves behind, though. So we see that, big burst of energy in a characteristic way. We know a positron must have been given off and then destroyed an electron somewhere. Is odd. So last but not least, then you got a gamma ray. So a gamma ray is just really high energy light. So being that it's actually light, it really has a 0 rest mass. It doesn't weigh anything. Light doesn't weigh anything. So it's a gamma ray. So it turns out, and we'll talk about it very briefly later, but just like an electron can be in the excited state, and when it goes from the excited state down to the ground state, it emits light. Well, it turns out a nucleus can also exist in an excited state. And if it drops down to a lower energy state, it emits light. It's just a lot higher energy light than we're used to seeing with electrons. So this is the really nasty stuff, or at least part of it anyways, but some of the really nasty radiation that you'll see given off that really messes people up. All right. So when you look at a particular nucleus, there are certain things you can look at and examine about that nucleus to see if it's going to be radioactive. Typically the way it works, so is an unstable nucleus is synonymous with a radioactive nucleus. A stable nucleus, less likely to be radioactive. So there's kind of this inverse trend between stability and radioactivity. So when we're looking for the radioactive nuclei, we're looking for the unstable ones. So there's pretty much 3 criteria we're going to typically look for to identify these unstable nuclei. So the first thing we're going to look for is an odd number of either Z protons or N neutrons. The very first thing you want to look for. So elements that have odd numbers of protons or neutrons tend to be less stable and therefore more likely to be radioactive. But it turns out that if you have an odd number of both protons and neutrons, you're almost almost definitely guaranteed to be radioactive. There are only 4 or 5 isotopes of any element that have odd numbers of both and are still stable, are still not radioactive. So if you've got an odd number of both, you're going to be radioactive. So you can typically get a question that might just say, which of the following is most likely to be radioactive? This is the first thing you look for. Just check out how many protons and how many neutrons it has. If one of them out of your choices has an odd number of both, he's your answer.
It's not likely to be one with an average, like chlorine.
So, well, in this case, they're always going to give you they're not going to give you the average atomic mass or something. They're going to give you a very specific isotope. So they give you just chlorine-35 or just chlorine-37. They wouldn't give you an average or anything like that. So always giving you specific isotopes. So the next thing you're looking for is what's called the N/Z ratio. So this N/Z ratio is the ratio of neutrons to protons. So it turns out, again, the protons hate each other. They repel each other. So you got to have a certain number of neutrons in the nucleus to kind of just buffer it, so to speak, to keep this nucleus and these protons from flying apart and then this nucleus from breaking up. So for the elements up through calcium, for atomic number less than 20 and up through 20, so they want to have an equal number of neutrons and protons. You don't want to be lower than this, you don't want to be higher than this. You want to be exactly equal for atomic numbers up through 20. But as you get larger and larger atomic numbers, so this N/Z ratio is actually going to start favoring a slight excess of neutrons. So, and for the very large one, it's going to approach 1.6. So this is tricky because, for atomic number 20, you want this N/Z ratio to equal 1. But for atomic number 22, it'll equal like 1.1. For atomic number 30, it might equal like 1.2. For atomic number 50, it might equal 1.4. And for the really large ones, it finally gets to be about 1.6. So it's hard to ask you about an appropriate N/Z ratio for atomic numbers higher than 20. Whereas for atomic numbers lower than 20, it's an exact number every time. And so this is where they're typically going to try and ask it to you, is right here. So for atomic numbers lower than 20, you want an equal number of protons and neutrons.
So nitrogen, for example, has 7 protons, 7 neutrons.
So he's one of the 4 exceptions. So, but they're not going to give you one of the exceptions on this list either, FYI. So the last thing you're looking for is what's called a magic number. So you guys have learned about magic numbers. We never called them magic numbers, but it turns out if you have a magic number of either protons or neutrons, you're more likely to be stable, having one of these magic numbers. So you guys learned about something similar to this with electrons. If you have a certain number of electrons, you're more stable. Those certain numbers would be like 2 electrons, or 10 electrons, or 18 electrons. Why are those more stable?
Filled valence shells.
Filled valence shells. Those are the noble gases. So there are certain magic numbers for electrons. We just never called it that. Well, it turns out there's various magic numbers for neutrons and protons. And there are certain numbers you don't have to memorize them. They're not going to ask you a question about that directly unless they supply you with the magic numbers. So if you need the magic numbers, they're going to be given to you. Typically, you're not going to see anything to do with magic numbers on the DAT. You may get a passage that talks about it on the MCAT, which is why I bring it up. So, but if you're just looking for, a standard question, you're typically going to look here first and here second. Not something you'll typically have to deal with. I only bring it up so that you're familiar with it in case you get in a passage on the MCAT. Cool. So we look at something like oxygen. And the specific isotope of oxygen we'll look at is oxygen 16. So oxygen 16, what's the atomic number for oxygen?
8.
8. So what is N for oxygen?
8.
What is Z?
8.
8. And so what's N over Z?
1.
1. So oxygen 16 is kind of our textbook example of a very stable nucleus. So does it have an odd number of protons or neutrons? No, they're both even numbers. So its N over Z ratio, well, its atomic number is 8, which is less than 20. And so what do I want its N over Z ratio to be? 1. 8 over 8 is indeed 1. It's exactly that. What's more, so 8 turns out as a magic number. It has a magic number of neutrons and a magic number of protons. It is doubly magic, so to speak. So having a magic number of both protons and neutrons, again, not something you have to deal with, but again, it's a very good textbook example of a very stable and very not radioactive nucleus. So we can look at what's called the belt of stability. So the belt of stability. The belt of stability shows a plot of neutrons versus protons. So it turns out that all the stable nuclei lie right along a narrow region on this graph. If you get too far off of this line, you're not a stable nucleus anymore. So it turns out that up through atomic number approximately 20, you want the slope here is 1, and you want a perfect 1-to-1 ratio of N over Z. But as you get higher than atomic number 20, it starts curving up for that slight excess of neutrons, showing that N over Z ratio increasing. So you might also see stability, so in a kind of a graphical representation with this belt of stability, and just knowing that all the stable nuclei lie right along this lovely line. So we'll talk a little more about this when we start talking about spontaneous routes of nuclear decay. All right, if we look at nuclear reactions in general, so your nuclear reactions kind of take on some general trends. So oftentimes you'll see this kind of general form. The parent nucleus will turn into a daughter nucleus. And you might also get some other particle present as well. So what you also always get as a product in a nuclear reaction, though, is energy. So nuclear reactions all give off energy, and typically a fair amount of energy. So, and again, this energy, hinted at it before, this energy comes from the fact that mass is converted into energy. So you will always have a little bit of mass converted into energy in a nuclear reaction, always. So who will weigh more, the parent or the daughter?
Parent.
So the parent, because turning into the daughter, it's got to lose a little bit of mass to account for that production of energy. So the parent nucleus will always be heavier than the daughter nucleus. So, and that's a little bit deceptive, as we'll see in a sec, but it's always a very small amount of mass that's lost. But again, a small amount of mass, if you look at this equation, take that amount of mass and you multiply by the speed of light squared, and that tells you how much energy it's been turned into, so to speak. And a small amount of mass, well, how big is the speed of light?
3 times 10 to the 8.
Yeah, 3 times 10 to the 8th meters per second. It's a huge number. You square it, it's even huger. So you take a little tiny bit of mass times a big, fat, huge number squared, and you get a lot of energy.
Is that in calories or joules?
It's in joules. So the actual calculation is not something you're likely to have to do a whole lot. We'll talk about some nuclear binding energy stuff and approximating some things, but the actual calculation itself, they're kind of limited on how specific they can get with you just because you don't have a calculator. All right, so let's talk about some specific nuclear reactions. So the first type of nuclear reaction, and you know what? I think I'm going to start on a fresh board for this, because this is going to take up some space. This is pretty much looking at the table on your handout. So these are your spontaneous routes of decay. The first is alpha decay. So alpha decay is also called alpha emission. So when something is emitted, it is a product in a nuclear reaction. So alpha decay is also called alpha emission. So if you look at the result of alpha emission, the result is a reduction of mass. So big fat reduction in mass. So and who wants to lose weight? The heavy elements. So it turns out that heavy nuclei just are not stable. This is why we have to stop at a certain point as far as the elements go. That's why the periodic table ends, because the higher the atomic number and the heavier these elements get, the less likely they are to be stable. So it turns out that if your atomic number is higher than 83, so higher than 83, so 84 and higher, you are radioactive. Every element with an atomic number higher than 83 is radioactive. So if you look at a standard periodic table, it's atomic number 84 that usually is the first element with an atomic weight in parentheses. It's in parentheses because it's an approximation. The thing is so radioactive that they can never get an accurate weight because it's decaying all the time and so quickly. So it's also often convenient for that reason as an easy way to remember where this cutoff occurs. So for these heavy elements, again, you're not stable if you're heavy, so they want to lose mass. Easiest way to lose mass is to do this alpha decay. Its main result is a big reduction in mass. Alpha particles have a mass of 4. You get one of those off, you reduce your mass right off by 4. So if we look at an example of alpha decay. Let's pick an element here. Let's look at, say, thorium. Let's look at thorium-232. Now let's have this thorium-232 undergo alpha decay, again, also called alpha emission. So this thorium, what we start with, is the parent nucleus. What's the atomic number for our thorium?
90.
90. And so if it undergoes alpha decay, it automatically has to produce a what?
Alpha particle.
Yeah, it's got to have an alpha particle as a product. Again, when something's emitted, it's a product. So with nuclear reactions, you've got to balance the mass numbers and the atomic numbers on both sides of the reaction arrow. So this is our parent nucleus. It gives off a little tiny particle. And what's left behind is the daughter nucleus. So based on the fact that we've got to balance the mass number and atomic numbers, what is the mass number of our daughter nucleus going to be?
28.
So, because 228 plus 4 is 232. What is going to be the atomic number? 88. Is indeed 88. Whose atomic number 88?
Radon.
Radon. So if thorium were to undergo alpha decay and emit one alpha particle, it would result in radon-228. So this demonstrates, one, what alpha decay is, but it also demonstrates how to balance a nuclear reaction. Again, the mass numbers and the atomic numbers have to balance. So you might be like, wait a minute, Chad. You said the mass numbers have to balance, but you just told us that all nuclear reactions lose a little bit of mass, which is turned into energy. So that is true. We've still got to balance the mass numbers. Remember, it's just a tiny bit of mass. The way this works, these are rounded to the nearest whole number. If we actually had the exact mass, if we actually knew that this was like 232.0746534 AMUs, and knew the exact mass of an alpha particle and the exact mass of this radon nucleus, so we'd see that the products have a little tiny bit less mass than the reactant. So we won't see it with the average, the rounded mass number here, but we would see it if we had the exact numbers. Cool, that's alpha decay. Should we stop there, Alan? So, one thing about sterics we didn't mention, directing something to go in between two substituents is not very likely. So here, this ortho position relative to the OCH3 has a substituent on either side. There's going to be a fair amount of steric hindrance blocking anything from ending up there. So we're definitely only going to go to this other ortho position.